Thanks for coming, everybody. Sorry for the delay there. It's early. Everyone's waking up. My name is Sam Friedman. I lead firmware engineering for Golioth. Golioth is a cloud device management platform for embedded devices. We work on Zephyr, which is why we're here. We also work on a couple of other platforms. My talk today, though, isn't about Golioth. It's about microservices for microcontrollers, composable software architecture for embedded systems. Also, I wanted to mention this is my first conference talk ever, so thank you for being here for this momentous occasion for me. All right, so if you've heard of microservices, you probably are wondering, like, isn't that a cloud thing? Why are we talking about them at an embedded conference? And it's true that as microservices, the term is like mostly known, it's a cloud thing, and it's also true that I chose that term to make my talk sound a little bit more interesting. But what we're really talking about here are just really modular software. In the cloud world, microservices are like very small individual pieces that can be deployed very quickly and very independently. And it's designed so that really large teams, like the big companies, don't need to coordinate thousands of engineers to release their web app every time they need to release it. They can release small pieces of it all the time. That's not usually a problem for firmware. You have to update the whole firmware all the time anyway, and our teams tend to be smaller. But we can still gain a lot of the benefits from, or a lot of benefits from using a sort of microservices-like architecture. What it looks like in firmware is, again, just very small, very loosely coupled, independent tasks. We'll talk more about what a task is. Communicating through well-defined IPC mechanisms. And so the analog there would be like, through a lightweight API. In the cloud world, we're just using IPC here in firmware. The benefits you get from that are similar to the cloud world. You can move faster because smaller things are easier to test. They're easier to understand. Things that are easier to understand are easier to maintain. And they're more isolated. So if you need to make a change into one part of your firmware, you're less likely to have that impact the rest of your firmware. That's just good software architecture, software practice, I think, for any software that you write. But the part that I want to stress is actually composability, and we're going to talk about that more here just in a minute. This is really why I think this architecture shines for firmware. So what is composability, right? You can think of it basically, you have a bunch of Lego bricks, a bunch of small pieces that you can assemble to create something bigger. Just like with Lego, if you have just a very simple brick, you can combine them to create very complex, very beautiful things, right? It's the same way of thinking of that for your firmware, right? You want to break things down to the smallest pieces so that you can pick and choose them. The reason they need to be small is that having smaller pieces makes them more reusable. If they only do one thing, then you can pick it up and use it. You don't have to worry about, is this going to bring in a feature I don't need? Is it going to have a dependency on a piece of hardware that I don't have because it's trying to do too many things? This little guy in the corner, we call him Echo. He's pointing right here because this is why that's really important for firmware. In the cloud world, when you deploy your new web app, the old version is basically gone, right? It's deleted. No one's ever going to use it again. All of us who make embedded devices know that's not how firmware works, right? Once you deliver a product into the field, that product needs to be supported until it's no longer being used, right? Even if you can update the firmware, your users may not choose to update it. And as you release new hardware versions, right, adding hardware, changing hardware, removing hardware, adding features, removing features, you still need to support the old versions of your product. Having composability allows you to use the same code because what you're doing now, instead of rewriting your firmware, which I've been part of a lot of teams who have changed one little thing in their hardware and rewrote the entire code base from scratch, instead of doing that, you're now just adding a piece, adding a software module, adding a task, removing a task. The configurability of it, the composability, is what allows you to reuse your code faster, better, while also getting all of the other benefits that we talked about earlier, including better testability and maintainability. All right, so what does that actually look like? We talked about tasks a little bit earlier. Tasks are these independent actors in a system. They need to communicate through IPC. One thing that I mentioned is lots and lots of small tasks, which if I might have made some of you think, like, well, I don't have memory for like 1,000 threads running. So we're also talking a little bit about event tasks, which are a way of having really small pieces of independent software functionality, but without using up all the resources of like a heavyweight thread for them. So tasks. Like I said, they are fine-grained, many, many small tasks. You want your tasks to be as simple as possible. They should really just do one thing, and you should think about them as I'm calling them business functions here, but essentially either a feature or hardware support to do one of those things. And they should be loosely coupled, which is something you've all heard before. The way I like to define it is no public interface. So there are no header files for tasks. You cannot call into them. They have no APIs at all. Instead, all communication is through IPC, through indirect IPC. So this means they're not exposing a queue that you put things into, but instead there's some other inter-process mechanism that allows these threads to communicate with each other without actually knowing with whom they're communicating with. And we'll get into that in a minute. And then these tasks, because in order to ensure that they can be added and removed at will, they all need to sort of be on the same footing, right? You can't have a main task which is trying to coordinate those tasks, because then you'll have to change your main task every time you add or remove a task. Doing hardware initialization in the task itself becomes difficult because if you have 3 tasks that are using the same driver and one of them sets it up, but then that's the one that you want to remove, now you have to figure out where else to initialize that driver. So I guess these are a lot of like prohibitions, which I think is maybe the main takeaway from how to think about this. It's how do we keep everything really self-contained? How do we keep everything as concerned with its one function as possible, so that when that function is no longer needed, we can remove the entire software component? Or similarly, when we add a new software component, because it's only concerned with its one function, we don't really need to make changes or the minimal set of changes to the rest of the firmware. And as I mentioned, tasks, we have those event tasks as well. So all threads are tasks, but not all tasks are threads. For IPC, there are a couple different ways that you could do this. I prefer PubSub, and this is not like a product, so I've capitalized it. This is just generally a communication paradigm that you can think about. I'm sure many of you are familiar with the basic concept, but you have topics and devices published to them, tasks published to them. Tasks can subscribe to them and receive messages. The important thing about it is that the focus here is on identifying that data, so naming the topic like accelerometer, or temperature, or GPS, or whatever. Sensor data is like the easiest one to think about, so it's probably going to over-index on that. And what the form of that data is, rather than on how modules are interconnected. There's going to be more concrete examples later, I promise. Right now, it's a lot of talking. And that's the important thing, right? So modules are communicating without knowing what the other party is. And that's important because now you can remove, change that party, add a new one without needing it. It's also important to note that this is many-to-many, and that's also important for like when you want to add a new feature that can like hook into an existing data stream, right? Like that's just naturally supported. This removes the inter-task dependency. So we mentioned that there's no public API. The reason why that's important, right, is again, because like if you stop compiling in a function that another module is calling, then you're going to fail to link. So these tasks don't communicate with each other. Their dependency is on PubSub. So PubSub has to be there. Whatever your PubSub bus is, needs to be there in the system. But that's pretty much the only direct dependency for the system. Another advantage of this, and again, I want to stress that like, for me, the main point of this is composability and being able to support multiple firmware products with one set of code. But there are a lot of other benefits too. One of them is removing developer dependencies, development dependencies. So if you are developing a module that communicates to and from PubSub, right, this kind of gives you a built-in abstraction barrier where you can easily inspect or inject data in order to test the module before the rest of the whole software is ready. And what's great is not just doing that when you are in development, but in testing later too, because these injection points basically don't go away. They're part of the actual core system. You can use them throughout the life of the product. So where I've used this in the past is like if you have any kind of UI on your device and that UI is triggered based off of events. If those events are pub sub messages, triggering your screen is really easy. You have a little CLI command that can just like fire off a pub sub message and trigger any screen you need, any animations, things like that. Similarly with pulling off data, you can just write a really simple application that just like opens up the accelerometer topic, reads it, prints it, and that becomes really easy to interact with. And then finally, the last task we were talking about are events. I think there's another corollary to the cloud here, which is cloud serverless functions are pretty similar. So I'm calling them threadless functions. It's multiple tasks. They run on one thread. These are essentially callbacks that execute in response to a pub sub message. So you register them against a particular message. They run on a shared thread. So they run to completion, right? And it's important to note that they are not tasks. So you need to be careful. Think about them maybe not quite as, as performant as interrupts need to be, but kind of in that vein, right? They can't block for a very long time, right? Any sort of operation like that is going to prevent other events from running. And so actually, this is probably a good point to talk about, like, how do you choose what is an event or a thread? Generally, anything that needs to like directly interact or wait on hardware is going to have to be a thread. Like most flash writes are going to, they can take a long time, so you don't want to do those network operations. Even some sensors you need to read from, in maybe like a polling manner, if there's any kind of delays in there, tend to be threads. And then more like pure business logic tend to be events. And again, these events, things you would use for events, are probably not things that would have been their own thread or their own task in like a traditional system that you might have built before. Because we're trying to really create a lot more tasks than you would normally see in order to create those small little Lego blocks and keep everything composable. And again, concrete examples coming. All right, this is the Zephyr Developer Summit. So how do we do this in Zephyr? ZBus is, I think, still relatively new, maybe about a year old. It's really great. This is Zephyr's implementation of a pub sub bus. The terminology that they use is a little bit different than what I was using before. Topics are channels. Messages can have data associated with them, which is great. The threads, so you can have what they call thread subscribers, which are the thread tasks that we talked about. It's not shown here. They can actually have a couple of different kind of messages. You can either like receive a copy of the actual message into your own queue, or you can receive a reference to a message. As far as like the architecture part of this, it's not really so important. They also implement what they call listeners, which is what I was calling events earlier. So that's really nice. You don't have to implement your own event thread or anything like that. That's already built into ZBus. And this takes a lot of the work and complexity for you. I highly encourage you to go listen to the Zephyr Tech Talk on ZBus. I think it was actually phrased or like positioned as kind of like a debate, like should you use ZBus, should you not use ZBus? All the Zephyr Tech Talks are great. This one's particularly relevant for this talk. The next thing is iterable sections. This is maybe a little bit like non-obvious about how important this is. I mentioned before that there's no public interface and there's no main thread coordinating which tasks are running, right? So how do these tasks actually get put into the system? Essentially, including a task is the same thing as compiling it, right? If you compile a task, then it gets into your build and it will run. The way that works is using iterable sections in Zephyr. What this is basically you place a struct into a particular linker section at build time, and then the linker grabs everything from that build section and puts them packed into into an order. And that essentially creates an array in Flash, and then Zephyr has facilities to like iterate through that. What this means is you can create basically, modules can register themselves. They can place themselves into global arrays without there having to be any kind of like central registry in your source code. Just by compiling it, the linker ensures that that's placed there. So Zephyr uses this for registering channels for ZBus, for registering the listener events. It uses it for task or for thread creation. Again, the importance of this, right, is that it prevents you from having that central piece of code that is orchestrating everything that you need to change every time that you want to create a new version of your firmware. Instead, all you do is you set a kconfig option or maybe change something in your CMake file to include or exclude a component, and that becomes the entire like building of the application, right? And then the last part of it is system initialization. So this also uses iterable sections, but I mentioned before, you can't rely on any task to do the initialization because you may remove that task. Zephyr has a really robust initialization system, which a lot of different levels. One of the things where in other systems, actually, this can get pretty hard is if you don't have a main task to ensure that you initialize things in the right order. Maybe your display needs the power regulator initialized first, things like that. If you're just kind of relying on like which threads run or it can be pretty difficult. Zephyr has initialization levels. They have initialization priorities within levels. All of this, again, done through those like iterable section structs that get placed in the linker. And this allows you to pretty fully specify the initialization order and what hardware and libraries need to be initialized in those libraries and drivers themselves. So your application doesn't need to do it. So by the time all of your tasks run, they're all ready to run, and they're all able to leverage the full capabilities of your system. And again, this is important because if you remove a task or if you add a task, you could be changing your initialization, which could cause complexities when you're building the various products on your one code base. OK, real-world example. That was a lot of talking, and I apologize. It's not how I like to do my presentations normally. But hopefully this will make everything feel a little bit more concrete. I want to talk about a cold chain asset tracker. This is actually a cold chain. This happens to be a reference design that my company Golioth makes. But I mostly chose that because I know there are no like copyright issues with this photo. So it's not important that my company makes it. What this is it's a little like GPS device with a temperature sensor and a cellular modem, and you put it in like your frozen food shipment, in the back of a refrigerated truck, and it ensures that throughout the process or throughout the shipping of your food, it never goes above freezing, so it hasn't spoiled, right? So this is a little block diagram here on the right side of that screen. The sort of rounded rectangles are tasks, and the diamonds are pub subtopics or ZBus channels. This is obviously simplified. There would be a lot more going on in the system normally, but for the purposes of this, I think this is a good example. So the GPS thread, these are actually all four of these tasks right here are threads in this contrived example, because I mentioned, right, like if you're dealing with hardware, you're generally going to need a thread, something that can block. So the GPS task is publishing to the position topic. The sensor's task is publishing to the temperature topic. Both are being consumed by the network thread. That's one of the simplified things. That would probably be a couple of different tasks. But both are being consumed by the network task in order to upload that data to some cloud database where you are tracking this, or maybe a visualization tool. And then also to display, so we can display that data locally. So that's sort of the base. But let's say your product manager comes back to you. They say, hey, we talked to the customer. They're tired of the drivers in the front. They're not looking at the screen. They have no idea when the temperature rises. We want to add a new feature that plays an alarm whenever the temperature rises above a set limit. So we can add a new task. This task is actually going to be an event task, or again, a listener in the ZBus nomenclature. What this task does is it just runs every time there's a temperature message, and it compares that to some threshold, right? And if it passes that threshold, then it publishes a message to the overtemp topic. So I just described to you the entire task, right? You can imagine that's probably like 4 lines long. Just to like emphasize that like tasks should be really, really small. That is a feature, that's a piece of functionality. That's all it should be. It's in its own C file. It has no public API. It's just that one function. But it is a task because it is that independent piece of functionality, and it's not going to take any extra resources on your system because it's going to run on that event processor thread. So it publishes to the overtemp topic, and then that overtemp topic is something I should have mentioned about this. So the arrows that show the data going, like position pushing data to network, it's sort of describing the flow of data, but remember that these tasks subscribe to that data. So they're actually calling into ZBus or your pub subsystem to say, hey, I'm interested in position data, right? So the display, we do have to change the display a little bit because we are changing the display. We're adding a new screen. So we have it register onto the overtemp topic. And we create a new screen that puts up maybe one of those little warning symbols. We also add a new audio task, which maybe plays a tone or a buzzer or something to audibly alert the driver. So that's great. That's our new thread. We had to change the display a little bit, but we changed it because we actually are changing it, not because it needed to be changed in order to support some other change, right? The sensor thread is now sending data to the alarm task, but we didn't have to change anything in the sensor task. We didn't change a single line of code there. So that's kind of like where this architecture shows its value. But I think it's even better when you delete something. So let's say, the product manager comes back and they say, hey, these are really expensive. We don't need a display. The driver's in the front. He can't read it. Why do we need a display? Let's delete it. Let's save some money. That's it. You delete it. You just delete the display task, and the rest of your firmware will still run. All these topics are no longer subscribed to by the display task, so they're no longer getting data. You no longer have to. So yeah, it's not running anymore. I actually spent quite a while trying to see if there was more to talk to on this slide, but I think that's kind of the point, right? Is once you've separated everything into these very distinct pieces of functionality, and once you've ensured that they are loosely coupled, you can remove things and it doesn't affect anything else, right? I've had the experience in the past of trying to remove a screen, like a piece of the UI, and when I hit build, the file system recompiled. So somewhere there's some weird dependency where the file system is depending on the screen. I never figured out what that dependency was, but when you build it up like this and through this system, that doesn't happen anymore. So that was it. Pretty quick. We have about, I think, 10 minutes left. Are there any questions? Yes, I don't know if we have a microphone in the mic.
Yeah, hi. Thank you for the talk. Just a question on how would you manage dependency initialization, especially if you have to initialize services at different times?
Sorry, could you repeat the first part of the question?
Yeah, how would you manage initialization priority? Mm-hmm. So for example, if the task you want to implement has several dependencies, right? And you're not very sure when these dependencies will finish initializing.
Yeah, that's a really good question. So Zephyr actually has built-in support for this. There are different initialization levels. I'm not going to get them all off the top of my head, but there are several different levels that you can do before the kernel boots, several after the kernel boots, some at what they call the application level. And then within that level, there's also, you can set a numerical priority, which I think is 0 to 99, or some other quite large range where if you need more than that, you're probably building a very complex system. And so you set those initialization priorities according to your system. A lot of them, may not be in code you can necessarily control. There might be modules that are in the Zephyr tree itself. A lot of those have kconfig options that you can set in order to change the priority if you need to.
Thank you.
Hey, great talk. Food for thought. Did you think about mixing the system with linkable, loadable extensions, so you could even like just have a small piece you can like push through the system or like small functionality?
Yeah. In relation to this kind of architecture, I haven't thought about it till right now. I think that's actually a really great question, because this can kind of enable that, right? Because it sort of, once you load that module, it can subscribe to these topics, and that doesn't necessarily need to happen at build time, right? So yeah, I think that provides, I guess, yeah, I think those work really well together. You'd have to be careful to, like, when you unload a module, to make sure that you unsubscribe from all the channels that it was connected to. But that's more of an implementation detail.
You may not know the answer, but performance of ZBus. For example, the products I'm re-architecting right now, we deal with sometimes, say, 6,000 messages per second going out of the device. And so we have to do all of the work to gather the data and collect it, so we're dealing with a higher rate than that internally. Do you think ZBus can keep up with that?
Well, I won't give you a definitive answer, because I don't know how fast your processor is and things like that. I will say that there is some overhead. It's pretty small. So I mentioned briefly that there are two kinds of ways you can subscribe to ZBus. And one is where ZBus will copy messages into your queue, and another one where it passes it by reference. I imagine if you're sending around 6,000, you're probably doing it by reference, so that is pretty performant. I've implemented a pub/sub architecture in the past where we used strings to describe the topic. So you had to do some string compares, which aren't the fastest and not too slow, but ZBus doesn't use that. They're using integer channel IDs that are defined at compile time through the linker, so that's pretty fast. So essentially, the other thing that I would say, and actually I'm not sure exactly how ZBus is implemented here, so take that with a caveat. The way I've implemented systems like this in the past is using like linked lists. So if you have the performance there grows with like the number of topics and number of subscribers you have. So if it's a high volume of messages going between a small number of tasks, that probably is not an issue. But if you have 6,000 tasks, then sending a message could take iterating through 6,000 subscribers. And again, I don't know how ZBus is implemented. Obviously, there are ways you can speed that up, sorts and searches and stuff.
So the reusable logic part is great. I'm wondering how, with like the iterable sections part, how that sort of handles reusing the same task. So say you had 3 temperature sensors and you've got a task which reads the temperature sensor and pushes it somewhere. If it's all sitting in the one C file, that doesn't, like, you can't create that 3 times, for example.
Right. So most of the entries in the iterable section have like a name. Or so basically the way this works is there's like a macro. One of the arguments of the macro is a name. So you could actually like instantiate that struct that describes that task multiple times. You would, it would be like temp sensor 1, temp sensor 2, temp sensor 3, but they would all have the same, they would all use the same function, so you could at least reuse that function call. And then most of these iterable sections also take like a context argument, right? Like a user void star, right? And so you could pass the context in there to say like, hey, you're actually reading from, this temperature sensor, that temperature sensor.
That's one big room.
Work cut out for you.
Hi, yes. I'm very new to Zephyr, so I don't know all of its capabilities. I was curious about your architecture concepts in relation to possibly multi-core usage. Is that of a play there, or?
That is a great question that I do not have the answer to.
Fair enough. But you wouldn't knock it out of the part. You wouldn't say it's a no or something like that.
Correct. I wouldn't. Most like inter-core IPC mechanisms kind of work with like a hardware mailbox anyway. So sure. I could definitely see extending ZBus to like use that as sort of like a backend. Right. But I've never like. Gotcha. Honestly, I've never really worked with like a SMP very much myself, right? When I've used 2 cores, it's been like this core does a very specific thing. So.
Gotcha, yeah. I work in SoCs all the time, so it's always how do you get them to work together? So
yeah.
It's interesting. Okay, thank you.
Thank you. Hello. Thank you for your presentation. If I understand well the pub/sub, you have a module or a task that is the publisher and another one that subscribes to it. So every time a publisher publishes something, the subscriber will be notified and do something with that information. But sometimes the subscriber doesn't want to be notified, or the subscriber wants to get the information when it's needed. For example, the over temperature alarm that you mentioned. That could be a situation where, oh, there's an over temperature. I want to know the position where it happened. So I'm interested in a position now. I don't want to be getting events all the time a new position is published. So does ZBus support that as well?
That's a really good question. That was some slides that I took out of the presentation, actually. I don't believe ZBus supports it, and I'm actually not aware of like a built-in library in Zephyr that does it, although anyone, please feel free to correct me. But what I usually refer to that is shared state, essentially, is what you're asking for there. And you can do something similar where you create a central module that can like hold shared state, and where you basically, it's similar to ZBus, you refer to that state by like an ID. So you're like calling into this module and you're saying like, hey, give me the the current state of this identifier, rather than like directly accessing the memory itself. There are a couple advantages of that. One is that this system can know whether or not that data exists or not, and that's important for like, let's say, you remove the task that sets location, right? You just care about the temperature, you're not doing position anymore. Well, you don't want to just, display junk data, right? You need a way to say, well, there is no position information, actually. The other thing is that it allows you to abstract away concurrency protections. So you can do all of the current concurrency protections, mutexes, whatever kind of lock you're using, within that module. So you don't need that in all of the tasks, which in my experience, some of the hardest bugs to track down are around concurrency. So if you can reduce the surface area of where those bugs can pop up, that's really helpful.
Thank you very much.
Hi, I actually have a follow-up on that question. What that sounded like was an RPC between 2 modules with a command and response. And I'm wondering, you mentioned not defining APIs for these modules, but typically a function like API surface is a great way to define an RPC. Can you speak to that trade-off of not defining an API for this, or how you go about that?
Yeah. So I will say, to be clear, I was not trying to describe an RPC before. More of like a file system, which I hesitate to say because it's not really anything at all like a file system, but saying like, give me the contents of foo.txt, right? More like that. For an RPC, I think you could do it, like RPCs can be decoupled. You generally still need to know sort of like who you're sending that request to, which can create a little bit more of a tight coupling. It's certainly less than if you're doing like a function call, right? And also, I think there's benefit in thinking of like the data flow, right, rather than like the execution flow of a function or of a program. And this gets into things like inversion of control, right, where it's like rather than like asking something to happen, you just say that like this thing exists and wait for somebody else who cares about it or not. So it's certainly, I would say RPCs are possible for sure. I'm not sure that like in an embedded system though, where you can link everything together anyway, that there's as much benefit from it as you get in like a cloud system where the main benefit from RPC is you know being able to like pretend that something very far away is actually very close to you.
I think we're slowly running out of time, so perhaps one more question and that's it. And I also looked the Discord if we have any questions there.
Thanks. Yeah, we've implemented something sort of similar in an architecture with that, and we use sort of shared states to sort of share between different things. But my question was about the, I guess the channels. Is there a way that a channel can know when you're publishing to a channel, you can actually know how many subscribers you've got? Because if you've got dynamic tasks that are being switched off, you know, suddenly you don't need the temperature or the accelerometer data anymore. It'd be great to be able to have that sort of publisher to be able to go, okay, well, no one's subscribed to me, so I'm just going to go down into low power mode and wait until somebody subscribes again. Does Zephyr channels allow for the publisher to know how many subscribers it has?
That's a really great question, and I agree that'd be a really useful feature, but I don't know the answer. Sorry.
Oh, okay, right. Thanks.
All right, so I think formally that's the end of the session, but of course I assume that you might have more questions. You can just ask them privately. I think we've had a little break now before the next talk, so if you could just thank the speaker.
Great.